Okay, so section 6.3, the sampling distribution of a sample count, which is going to be the normal approximation to the binomial. So again, a couple words that should be familiar to you: normal for our normal distributions and binomial for binomial random variables. So we're going to put those two ideas together in this chapter on sampling distributions. Okay, so here's the definition for a sampling distribution. So the sampling distribution of a sample count x describes the distribution of values taken by the sample count x in all possible samples of the same size from the same population. So when we take a look at this sample count x, remember this is like the number of successes. So we're measuring successes. Remember, binomials, B stands for binary. There's either a success or a failure. Only two options. Now, there's an important note here, not really important for our class, but it should be talked about. We can ignore the violation of the independence condition caused by sampling without replacement whenever the sample size is less than 10% of the population. This is what's going to make us approximately normal, not just or approximately binomial, not exactly binomial. So if you remember from section, I think 5.3, there was this BINS acronym for a binomial setting, and the I did stand for independent. And if you recall, a couple of the examples that did not follow the binomial setting were because things were picked without replacement. Well, the idea here is that if our sample size is less than 10%, instead of picking each idea in our sample one by one, we can pick them all at once because they're so small, they're such a small part of the population that they're really not going to affect the population that much. Okay, so that's the idea. I will talk about it in our first example, but you don't have to really worry about it going forward. Okay, so when we have these sampling distributions, we need our center and we need our variability. So here's where the mean of the sampling distribution and the standard deviation of the sampling distribution for x, or the sample count, is going to come into play. So suppose x is your number of successes, sample size n, proportion of success p. The mean of the sampling distribution of x is mu sub x equals n times p. That's the same formula as the mean of the binomial random variable. The standard deviation of the sampling distribution of x is sigma sub x equals the square root of n times p times 1 minus p. That's the same standard deviation formula for the binomial random variable. And again, note that this is not appropriate when the sample size is more than 10%, too large. Okay. So again, this is chapter 5 coming back at you. Okay, example 1 says how many flash drives are defective? 2% of the flash drives in a shipment of 10,000 flash drives are defective. An inspector randomly selects 10 flash drives from the shipment and records x equals the number of defective flash drives in the sample. Part A, calculate the mean and standard deviation of the sampling distribution of x. So we're going to calculate the mean. The mean is mu sub x. Got ahead of myself. That's the mean. And the standard deviation is sigma sub x. So to do this, we need n and p. So what is my n? What is my sample size? Well, my sample size is the 10 flash drives selected, and my p-value is the proportion or percentage that are defective, because defective in this case is our success. Well, that was given to you right here, 2%, 0.02. So to find the mean, we're going to, before I get into this, I also want to show you this idea of, 10% of the population. So in this case, the population is 10,000. That's our population. And our sample size is 10. That's our n. So if you take 10 divided by 10,000, you're going to get 0.001. That is 1%. You are less. The sample size n is less than 10% of the population. So we're good to go. Okay, we can assume this is approximately binomial. So we can use the two formulas, n times p. When you do this, you get 0.2 defective flash drives. So almost still, close to 0 defective flash drives, just a small amount. And then to find sigma, we'll do 10 times 0.02 times 1 minus 0.02. Okay, and I'll go ahead and show that in our graphing calculator. So all this is going to go away. Okay, Desmos graphing calculator here. So we're doing the square root of 10 times 0.2, times 0.02. I'm sorry, times 0.02. Hopefully I did that right. Times 1 minus 0.02. And there we go. Let's round to 3 decimals. So 0.4427. The 7 rounds the 2 up to a 3. 0.443. That is our standard deviation. Okay. So our sigma sub x is 0.443 defective flash drives. Notice I put defective because I want to be as specific as possible, right? Defective flash drives. I'm going to use some shorthand uh, to go a little faster. Okay, so now it says interpret the standard deviation. Well, remember the two key words for standard deviation are typically varies. Okay, now we're going to make this a little bit more elaborate because again, we want to talk about how many we're choosing and doing it many times. So we're going to say something like this: if the inspector, let me find my pen. There it is. If the inspector took, and now here comes the definition of a sampling distribution, took all possible samples. And this is me just trying to emphasize what a sampling distribution is. All possible samples of size 10 from this shipment. So from the population, this shipment of 10,000 flash drives. So that's the setup, right? If the inspector took all possible samples of size 10 from this shipment of 10,000 flash drives, the number of defective flash drives, because that's what we're measuring, right, would typically vary, will typically vary, typically varies, whatever you want to say, would typically vary by about 0.443 from the mean of 0.2. And there's our interpretation. The number of defective flash drives would typically vary by about 0.443 from the mean of 0.2. All right, so there's objective 1, a little bit of review from chapter 5. All right, objective 2 is coming up, and I think you start with an activity.